The local evening news reports that a wildfire has consumed exactly 135 acres of timber just 13 miles east of Flagstaff, Arizona. That is not the real story. The cameras are pointed at the smoke. The maps on the screen show the perimeter. The anchor reads the acreage figure, mentions the red flag warning, thanks the fire information officer, and moves on to the weather segment. But what is happening above that perimeter, what is descending from a height that no ground camera can capture, is the actual emergency. There is a column of air pressing down on the Coconino National Forest right now that traditional firefighting was never designed to confront. It is invisible. It is silent. It is rewriting the rules of containment in real time, and almost nobody on television has said the words out loud. Stay with me, because once you see what is actually driving that invisible column from the edge of space, you will not be able to look at a summer forecast the same way again. If this has you thinking, subscribe to Rupture, because the surface story is almost never the real story, and we go where the evening news will not. Drop a comment below. When was the last time a weather report explained to you what the air above the ground was actually doing? By the time local emergency dispatchers received the first panicked phone calls on Monday afternoon, the fire environment in northern Arizona had already locked into a highly dangerous state. The conditions did not build slowly. They did not warn the way late spring fires usually warn. The air was waiting for an ignition source, and when it found one, the response window collapsed faster than the standard playbook allows. By 2:47 in the afternoon on June 8, 2026, the first smoke column was visible from the parking lot of a gas station on Townsend-Winona Road, climbing through the pine canopy at a rate that veteran dispatchers in Coconino County had not seen this early in the season since the tunnel fire of 2022. The location matters. The fire was burning just over a dozen miles outside Flagstaff city limits, inside the boundary of the Coconino National Forest, on a ridge of mixed conifer and pinyon juniper that climbs from roughly 800 feet at the base to over 8,000 feet near the crest. This is not flat country. It is not low desert. It is high elevation forest sitting on volcanic soil, fed by snowmelt that ran thin this year and rainfall that simply did not arrive in May. The fuel was already prepared. The slope was already steep. The wind was already wrong. Let me show you what the dispatch logs captured in those first 90 minutes. The initial report came in as a smoke check, which is firefighter shorthand for an unverified column that may or may not be a real ignition. By 3:02, the first engine from a Forest Service station along Highway 89 had eyes on the fire and reported active flame in the canopy of a single ponderosa pine. By 3:18, that single tree had become a quarter-acre patch. By 3:41, the patch had become 4 acres. By 4:15, it was 23 acres. The progression was not linear. It doubled, then doubled again, then jumped in a way that doubling cannot describe. The Coconino National Forest is the largest contiguous ponderosa pine forest in the world. That is not a marketing line. It is a fuel load statement. There are roughly 1.8 million acres of timber stretched across the Mogollon Rim and the San Francisco Peaks, and in dry years that fuel becomes a continuous bed, waiting for the right combination of heat, low humidity, and wind. Local dispatchers know this. They have lived with it for decades, but what they were seeing on Monday afternoon was not the standard early summer pattern. The standard pattern, the one the public is used to, looks like this. A fire ignites in mid-afternoon when humidity is at its daily low. It pushes with the prevailing wind. It slows at night when the temperature drops and relative humidity climbs. Crews work the flanks during the cooler hours, lay containment line by dawn, and the fire calms down enough by morning for aerial assets to do their work. That cycle, the daily breathing pattern of a wildland fire, is the foundation of how the Forest Service plans its response. The Papa fire did not breathe. By 6:00 in the evening, when the relative humidity should have been climbing back toward 30%, it was still sitting at 8. By 8:30, when the wind should have been easing as the surface temperature dropped, gusts were registering at 52 miles per hour on a remote automated weather station northeast of the incident. By 10:00, the fire had not lain down. It had not even slowed. It was throwing embers nearly a mile ahead of the main front, and the spot fires those embers created were merging back into the parent fire faster than ground crews could reach them. This is where the deviation from standard seasonal models becomes important. The National Interagency Fire Center publishes a significant fire potential outlook every month, and the June 2026 outlook had flagged northern Arizona as above normal for fire risk. But the language used was the standard cautionary language used in every dry June. It did not anticipate what was sitting above the forest. It could not have. The mechanism driving the Papa fire was not in the fuel model. It was not in the surface weather forecast. It was operating from a layer of the atmosphere that the public-facing fire weather products do not visualize. A retired hotshot superintendent who spent 31 years working fires across the Southwest, now living in a small home in Doney Park just outside Flagstaff, watched the smoke column from his back porch on Monday afternoon. He told a local reporter the next morning that the column had a shape he had only seen 3 or 4 times in his career, a flat anvil top with a hard right shoulder lean that meant the upper-level winds were not just strong. They were behaving like a horizontal river overhead, shearing the smoke into a pattern that signals deep atmospheric instability above the fire. He did not need a satellite image to know what was coming. He had seen the shape before. He went inside and started packing. The Forest Service Incident Management Team activated a Type 3 organisation within the first 6 hours, which is faster than normal for a fire of this acreage. A Type 3 designation means the fire is too complex for a local engine boss to manage with the standard resources of the home unit. It requires a dedicated incident commander, a planning section, and pre-staged resources for a multi-day operation. The fact that they jumped to a Type 3 organisation at 135 acres, rather than waiting until the fire crossed the 1,000-acre threshold, tells you what the people on the ground were already seeing. They were not managing the fire that was burning. They were preparing for the fire they expected. The first evacuation notices went out to a small cluster of residences along Forest Road 510 by 7:00 in the evening. These are not subdivisions. These are scattered properties, many of them seasonal cabins. Some of them year-round homes owned by retirees who moved to the high country for the cooler summers and the quiet. The notices were precautionary at first, then mandatory by sunset, then expanded twice more before midnight. A married couple in their late 60s who had retired from a school district in Phoenix and bought a small log home off Forest Road 510 in 2018 packed 2 suitcases, their dog and a folder of insurance documents into a Subaru Outback and drove to a relative's house in Flagstaff. They did not know if their home would still be standing in the morning. The wind by then was doing something unusual. It was not gusting and lulling the way evening winds normally do in the high country. It was sustained. A steady, dry, pressing wind that did not seem connected to any visible weather system on the standard surface map. The local National Weather Service office in Flagstaff had issued a red flag warning for the entire region, with the standard language about low humidity and gusty winds and critical fire weather conditions. But the warning, written in the format the public has been trained to scan, did not capture what was actually happening above the warning area. Ground crews working the southern flank of the fire reported something they kept noting in their radio traffic, which was later reviewed by analysts and quoted in early incident reports. They said the air felt wrong. They said it did not feel like dry desert air. It felt like the air from a clothes dryer vent, hot and arid in a way that surface humidity alone could not explain. One crew boss, a veteran of more than 2 decades on fires across the West, radioed back to operations and asked whether the spot weather forecast had factored in upper-level subsidence. That single question, buried in hours of routine radio chatter, was the first verbal acknowledgement from the field that something other than surface weather was running this fire. The fuel moisture readings tell the same story in numbers. Live fuel moisture, which measures the water content of standing vegetation, was running at roughly 71% for ponderosa pine, a value that is on the dry side for early June but not historically alarming. Dead fuel moisture, however, the moisture content of fallen needles and small twigs on the forest floor, was clocking in at 3% in some samples. 3%. That is drier than kiln-dried lumber. That is drier than the cardboard in a sealed shipping box. That is fuel that does not need to be encouraged to burn. It only needs to be touched. A piece of context here. The standard threshold for extreme fire behaviour, the one used by fire behaviour analysts across federal land management agencies, treats dead fuel moisture below 5% as a critical danger zone. The Papa fire was burning in fuel that was already 2 points below that critical threshold before the first ember left the canopy. The fire did not have to work for its growth. The forest had been preconditioned by something operating from above. By midnight on the first day, the fire had grown to its officially reported 135 acres, but the perimeter was no longer a tight oval. It was a long-fingered shape with 3 active heads, each pushing in a slightly different direction, each generating its own column of smoke, each throwing embers far enough ahead of the front that ground crews had stopped trying to anchor and were instead being repositioned to protect structures. The strategy had shifted within the first 10 hours of the incident. They were no longer fighting the fire, they were trying to keep it from finding the next subdivision. The Coconino County Sheriff's Office posted a brief social media update at 11:47 in the evening, listing the evacuation zones and the location of an emergency shelter at a community centre on the west side of Flagstaff. The post received the standard mix of thank you comments and prayers and questions about specific neighbourhoods. Nothing in the post hinted at what was driving the fire. Nothing in the local television coverage, which led with the acreage figure and a brief interview with a fire information officer, hinted at it either. The story being told to the public was the story of a 135-acre fire burning in dry timber under windy conditions, which is a story every viewer in the West has heard 100 times. That is not the story. The story is that the air above northern Arizona on the afternoon of June 8 was behaving in a way that the public weather products were not equipped to show, and the fire on the ground was simply the visible consequence. The flames were the symptom. The diagnosis was sitting in upper air data that almost nobody outside a few meteorology offices was reading in real time. And by the time the second day began, the people who did read that data were already realizing how much trouble the standard playbook was in. Remember where we left it, with ground crews rushing toward a 135-acre blaze during active red flag warning conditions. The crews had their orders, the dispatch logs were running. The evacuation notices were going out. The surface weather map looked the way these maps usually look on a bad fire day, with the standard symbols, the standard isobars, the standard colour shading for temperature and humidity. Everything on that map made sense to anyone who has ever watched a local weather broadcast. But the map was missing the story. Let me walk you through what the public sees when they pull up a weather product on a phone or a laptop. They see a temperature reading. They see a humidity percentage. They see a wind direction with an arrow and a speed in miles per hour. They see a precipitation forecast for the next several days. If they are more sophisticated, they may pull up a radar loop or a satellite image. All of those products are surface-oriented or near-surface-oriented. They describe what is happening within roughly the first few thousand feet of the atmosphere. They do not describe what is happening at 15,000, 25,000, or 35,000 feet above the ground. That distinction would not matter on a normal day. On a normal day, the surface conditions are a fair reflection of what is happening in the lower atmosphere, and the lower atmosphere is where weather lives. But on the day the Papa fire ignited, the surface map was lying. Not deliberately. Not because anyone wanted to deceive the public. It was lying because the surface map was never designed to show what was actually driving the conditions on the ground that afternoon. The wind gusts being recorded at remote automated weather stations across northern Arizona on Monday afternoon were not behaving like standard horizontal surface winds. They were registering at 50 to 65 miles per hour, but the direction was wrong. The standard summer pattern in northern Arizona produces winds out of the southwest, driven by the pressure differential between the Sonoran Desert to the south and the cooler highlands to the north. On Monday, the winds were coming from the west and west-southwest, but with a downward component that the surface anemometers could not measure. The wind was not just moving across the landscape, it was pressing down on it. A standard anemometer, which is the spinning cup device mounted on a pole at most weather stations, measures the horizontal component of the wind. It does not measure the vertical component. If a column of air is sinking, the anemometer will read the horizontal flow that accompanies that sinking motion, but it will not tell you that the air is descending. That information has to come from upper air observations, from weather balloons released twice a day at fixed locations across the country, from satellite-based atmospheric profilers, and from a numerical weather model output that integrates all of those data sources into a three-dimensional picture. The Flagstaff office of the National Weather Service had access to all of those products. So did every regional forecast office in the southwest. The data was not hidden. The data was sitting in the standard operational feeds that meteorologists pull up every shift. But the data was not making it into the consumer facing weather products in any form that the average viewer could pass. Here is the household scale way to picture what was happening. Imagine you have a closed room with a ceiling fan running. The fan pushes air down. As that air descends, it spreads out across the floor, and you feel a breeze at your feet. If you only had a wind meter at floor level, you would record a steady breeze blowing outward from the centre of the room. You would not record the fact that the air was originally coming down from above. You would see the horizontal symptom. You would miss the vertical cause. Now scale that up to a region the size of northern Arizona. The ceiling is the upper troposphere, around 30,000 feet up. The fan is not a single fan, but a broad zone of sinking air covering hundreds of square miles. The breeze at your feet is the 50 to 60 5-mile-per-hour wind being recorded at the surface stations. The cause, the descending column, is invisible to anyone watching the surface map. This is where the breakdown of typical regional weather patterns becomes critical. In a normal June pattern in the southwest, the upper atmosphere is dominated by what meteorologists call a subtropical ridge, which is a broad zone of high pressure that suppresses storm development and produces hot, stable weather. Under that ridge, surface heating during the day produces afternoon thunderstorms in the mountains, and the diurnal cycle, the daily breathing of the atmosphere, remains intact. Mornings are calm, afternoons are warm with scattered storms, evenings cool down, overnight humidity recovers. That pattern had broken. Sitting upstream of Arizona on Monday morning, embedded in the larger flow pattern across the western United States, was a long-wave trough, which is a southward dip in the jet stream that brings cooler air down from higher latitudes. Just east of that trough, where the jet stream was beginning to curve back northward, was a zone of pronounced upper-level descent. That is the geometry that creates the conditions for what meteorologists call a dry slot. The long-wave trough was the trigger. The descent zone was the consequence, and the consequence was sitting directly over northern Arizona on the afternoon the Papa Fire ignited. The viewer watching the local news on Monday evening did not see any of this. The graphics on the weather segment showed temperature numbers, humidity numbers, and a wind arrow. The forecast for Tuesday showed more of the same, with a small note about red flag warning conditions continuing. The viewer was given no reason to think that the air itself, the column of air sitting above their roof, was behaving in a way that the surface readings could not capture. A married couple in their early 60s, watching the broadcast from their living room in a suburb on the west side of Flagstaff, made a decision that night that thousands of households across the region were making. They decided the fire was 13 miles away, the wind would shift by morning, and there was no immediate reason to leave. They were following the information they had been given. The information they had been given was accurate as far as it went. The problem was that it did not go far enough. This is the gap that investigative reporting is supposed to close. The local news has a tight broadcast window. The weather segment runs 2 to 3 minutes. There is no time to explain upper-level dynamics. There is no time to walk a viewer through the difference between horizontal and vertical wind components. The weather presenter, who in most markets is a trained meteorologist with a real degree, knows what is happening above the surface. But the format does not allow that knowledge to reach the audience. The audience gets the surface map. The audience gets the highlight reel. The technical term for what was happening upstream of Arizona is upper-level divergence, which is to say that the air at the top of the troposphere was spreading outward, creating a sort of suction effect that pulled air upward in some regions and pushed it downward in others. Where it pushed down, over Arizona, the descending air compressed and warmed as it sank. This is basic atmospheric physics. Compressed air heats. Heated air dries. By the time that air reached the surface, it had warmed by several degrees and lost a significant fraction of its moisture content, simply because it had travelled vertically through the atmosphere. In other words, the air that was hitting the forest floor on Monday afternoon was not air that had originated near the ground. It was air that had originated miles above the ground and had been dehydrated by the journey down. That is why the dead fuel moisture readings were at 3%. That is why the live fuel moisture was dropping faster than the seasonal trend would predict. That is why veteran firefighters were saying the air felt wrong. The air felt wrong because it was wrong in the sense that it did not belong at the surface. It had been forced down to the surface by a process that was operating thousands of feet above the visible landscape. There is a piece of historical context that helps anchor this. In April of 1996, a fire near Buffalo Creek, Colorado, exhibited a similar pattern of unexpected acceleration under conditions that the surface weather products did not flag as exceptional. Post-incident analysis revealed that an upper-level dry intrusion had descended over the fire area in the hours leading up to its explosive growth. The post-incident reports, which were published years later in technical fire weather journals, became one of the early case studies that established the operational importance of monitoring upper-level dynamics during wildfire incidents. The lesson was learned by the meteorology community. It has not yet been translated into the public weather products that ordinary viewers see. A satellite image of the western United States on Monday afternoon would have shown the descending zone clearly to a trained eye. There is a specific signature in the water vapour channel of geostationary weather satellites that reveals zones of upper-level descent visible as dark, dry streaks against the brighter, more humid background of the surrounding atmosphere. On the afternoon of June 8, that dark streak was sitting directly over northern Arizona, narrow at its source over the eastern Pacific, and broadening as it descended over the Colorado Plateau. It was visible. It was on the operational satellite feeds. It was not on the evening news. The standard wind gusts being reported in the public bulletins, the 50 to 60 5-mile-per-hour figures that were showing up in red flag warning text, were the surface symptom of this descending column. The wind was not blowing across the landscape from some distant high-pressure system. The wind was being delivered downward onto the landscape by the dry slot above it. That distinction is not academic. It changes how the fire behaves. It changes how containment works. It changes which strategies have a chance of succeeding and which do not. The viewer is left to ask what force was manipulating the local atmosphere on Monday afternoon and into Tuesday. The answer is not a single force. It is a chain of processes that begin in the jet stream miles above the surface and end at the boots of a hotshot crew trying to lay a containment line on a steep slope of dry timber. The chain is not visible. The chain is not on the public map. But the chain is the only thing that explains what was happening on the ground. And the next piece of this investigation is going to take you inside that chain and show you exactly how it works. Let me introduce you to an invisible atmospheric phenomenon that can overpower an entire army of wildland firefighters in a matter of minutes. It does not have a dramatic name. It does not appear on the weather segment of the local news. It is described in operational forecast discussions in a single line of jargon that the public is not expected to read. And yet it is the single most important variable in understanding why some wildland fires explode and others stay small. The phenomenon is called a tropospheric dry slot. A tropospheric dry slot, which is to say an invisible column of upper atmosphere air behaving like a massive downdrafting vacuum, is a region of the atmosphere where dry air from the upper troposphere or lower stratosphere is being forced downward toward the surface. The word tropospheric refers to the layer of the atmosphere where weather happens, extending from the ground up to roughly 35,000 feet at mid-latitudes. The word slot describes the geometry, which is typically a narrow band rather than a broad area. The word dry tells you the most important thing about the air inside that band. It has almost no water vapour. It is, for practical purposes, desert air at altitude being delivered to the surface like a payload. Picture a household appliance to anchor this. A commercial dehumidifier, the kind contractors use after a flooded basement, pulls moisture out of the air and exhausts dry, warm air back into the room. Now imagine that dehumidifier the size of a small county, mounted 30,000 feet above your house, with its exhaust pointed straight down. That is the functional behaviour of a tropospheric dry slot when it couples to the surface. It is not weather in the way the public understands weather. It is an atmospheric mechanism that delivers desiccated air to ground level whether anything else is happening or not. The mechanism works through a sequence of steps that physicists understand well. Air at the top of the troposphere is cold, dry, and moving in patterns shaped by the jet stream. When the jet stream curves in a particular way, with a southward dip followed by a northward curve, the geometry of the flow creates zones where upper air is forced downward. As that air descends, it does not pick up moisture, because there is no moisture available to pick up at altitude. Instead, it compresses under the increasing pressure of the lower atmosphere. Compression heats the air. Heating reduces its relative humidity even further. By the time the descending air reaches the surface, it can be 10 to 20 degrees warmer and dramatically drier than the air it displaces. This is the part that matters for fire behaviour. The fuels on the forest floor, the dead needles and twigs and small woody debris, exchange moisture with the air around them. When the air is humid, fuels absorb moisture and become harder to ignite. When the air is dry, fuels release moisture and become easier to ignite. The exchange happens fast for fine fuels, within minutes for the smallest particles. A pine needle on the forest floor can shed a significant portion of its moisture content in under an hour if the air around it is dry enough. When a tropospheric dry slot couples to the surface over a forest, the fine fuels on the forest floor are essentially placed inside a giant low humidity chamber. They dry out faster than the natural daily cycle would predict. They dry out further than the seasonal trend would suggest. They become fuel that will accept ignition from almost any source, and once ignited, will release energy at a rate that the standard fire behaviour models did not anticipate. This is why a fire that should be at the early end of its life cycle, at 135 acres on its first afternoon, can begin to throw embers a mile ahead of the front. This is why containment lines that should be holding under normal conditions fail under dry slot forcing. This is why ground crews can do everything right and still lose ground. The mechanism is operating from above the canopy, from a layer of the atmosphere that no firefighter on the ground can see, touch or counter. That is not weather. That is a system telling you that the conventional model of how fires behave has been overridden. Let me walk you through the historical data, because the dry slot mechanism has been observed and documented on some of the most destructive wildland fires in the American West. The case studies span decades. The pattern is consistent. The same atmospheric signature shows up over and over again in the post-incident reports of fires that exhibited explosive, unexpected growth. In June of 2002, the Hayman fire in Colorado consumed more than 138,000 acres and destroyed 133 homes. The post-incident weather analysis identified a strong upper-level dry intrusion in the hours leading up to the most extreme growth period. The fire grew by nearly 60,000 acres in a single day, a rate that surface weather conditions alone could not explain. The dry slot above the fire delivered air with relative humidity values below 8% to the surface, and the resulting fuel response produced fire behaviour that ground crews could not engage. They withdrew. They protected structures where they could. They watched the rest. In May of 2000, the Cerro Grande fire near Los Alamos, New Mexico, destroyed 235 homes and threatened the Los Alamos National Laboratory. The fire began as a prescribed burn that escaped containment. The escape happened during a period of unexpectedly dry air at the surface, which was later traced in post-instant analysis to a descending upper-level air mass. The fire crossed the laboratory boundary in conditions that had not been forecast at the surface but were visible in the upper air data to anyone who knew where to look. In June of 2011, the Wallow Fire in eastern Arizona burned more than 538,000 acres. The post-instant weather report explicitly identified periods of upper-level subsidence as drivers of the most aggressive growth phases. The fire became, at the time, the largest in Arizona state history. The mechanism behind its growth was the same mechanism that was sitting over the Papa Fire on June 8, 2026. The pattern is not new. It is not rare. It is not something that the meteorology community discovered last year. The pattern has been documented for at least 3 decades in the technical literature, with the case studies piling up year after year, each one adding another data point to a picture that has been consistent for as long as anyone has been measuring it. The dry slot is not a theoretical construct. It is a recurring, measurable, repeatable feature of the atmosphere that has been responsible for some of the most catastrophic fire outcomes in modern American history. So why is it not in the public weather report? The honest answer is that it has not been translated. The mechanism is well understood at the operational level inside the National Weather Service, the Forest Service, and the academic meteorology community. The mechanism is incorporated into the spot weather forecasts that are issued to instant commanders during active fires, but the mechanism has not made the jump from operational forecast products to consumer weather products, because the consumer products are built around the assumption that surface conditions are an adequate representation of what the atmosphere is doing. That assumption was reasonable in 1980. It is no longer reasonable in 2026. The reason it is no longer reasonable is that the frequency and intensity of dry slot coupling events appears to be changing. The technical papers from the past decade have begun to document an upward trend in the number of days per fire season when upper-level subsidence reaches the surface with sufficient intensity to override the diurnal humidity cycle. The trend is not yet a settled finding. The data is still being argued over in journals, but the operational reality on the ground is that fire weather forecasters are seeing the signature more often, on more fires, in more regions, than the textbooks of 20 years ago would have predicted. There is one piece of context that ties this directly to the day the Papa Fire ignited. The dry slot that was sitting over northern Arizona on June 8 was visible on the water vapor satellite imagery as a dark, hard-edged streak running from the eastern Pacific across the Great Basin and into the Colorado Plateau. The streak was narrow at its source and broader at its destination, with the surface impact concentrated in a region that extended from southern Utah through northern Arizona and into northwestern New Mexico. The fingerprint was clear. The location was specific. The duration was forecast to extend through at least the following 48 hours. A retired forest ranger, who spent the last 15 years of her career in a fire lookout tower on a peak south of Flagstaff and now lives in a small house in the town of Williams, was watching the satellite imagery on Monday evening on her home computer. She had subscribed to a meteorology service after retirement, partly out of habit, and partly because she wanted to keep an eye on the country she had spent her life watching from a fire tower. She saw the dark streak. She knew what it meant. She called her former district supervisor on the phone and asked whether the dry slot was being factored into the strategic planning for the Papa Fire. She was told that the spot weather forecast had flagged the upper-level dynamics. She was not told whether that flag had reached the level of public communication. It had not. The household-scale comparison is the one that anchors this for the audience. A tropospheric dry slot operating over a forest is functionally identical to leaving a giant industrial heater pointed at a stack of kindling. The kindling does not know that the heat is coming from above rather than from the side. It does not care. It only knows that the moisture it was holding is gone, and that any spark from any source will now find a fuel that is ready to burn. The forest floor under the Papa fire on Monday afternoon was that stack of kindling. The dry slot above it was the heater. The fire that resulted is the visible part of the story. The dry slot is the invisible part. And the rest of this investigation is going to show you what happens when the institutions responsible for managing wildland fire confront a mechanism that the institutional playbook was never built to handle. In 2017, a technical paper published within the Proceedings of the American Meteorological Society changed exactly how researchers view sudden fire acceleration in the American Southwest. The paper was not a press release. It was not aimed at the public. It was a peer-reviewed technical document presented at a professional conference, sitting inside a thick volume of proceedings that gathers dust on the shelves of university libraries and is read mainly by other meteorologists and fire behaviour analysts. But the content of the paper, once you translate it out of the technical language, is the single most important piece of evidence supporting everything this investigation has laid out so far. The paper was authored by Fred J. Schoeffler, a former wildland firefighter and incident management team member whose career spanned decades on fires across the western United States. Schoeffler did not come to atmospheric science from a university research program. He came to it from a lifetime of watching fires behave in ways the forecasts had not predicted, and from a personal commitment to figuring out what was actually driving the discrepancies between the forecast and the field. He spent years collecting case studies, reviewing post-incident reports, and cross-referencing surface fire behaviour with upper-air data from the same days and same locations. What he found, and what the paper documents in detail, is that a specific category of catastrophic southwestern wildland fires share a common upstream signature. The signature is the descent of a dry, fast-moving air mass from the upper troposphere into the boundary layer where the fires were burning. The descent was visible in the upper-air observations. It was visible in the satellite water vapour imagery. It was visible, in retrospect, in the operational model output that had been available to forecasters in real time. But in fire after fire, the surface forecasts had not communicated the upper-air signal in a way that translated into actionable warnings on the ground. The paper documents this pattern across multiple historical fires, with the kind of methodical case-by-case treatment that professional meteorology requires. Each case includes the surface weather observations, the upper-air observations, the satellite imagery, the fire behaviour reports, and the post-incident analysis. Each case shows the same fingerprint. The fingerprint is the dry slot. The fingerprint is consistent. The fingerprint is documented at the institutional level by an organisation that does not make claims lightly. The American Meteorological Society is not a fringe organisation. It is the professional association that represents the meteorology community in the United States, with a membership that includes researchers, broadcast meteorologists, government forecasters, and private sector weather professionals. Papers published in its proceedings have been reviewed by other meteorologists. They are not opinion pieces. They are technical documents that have been accepted by the scientific community as legitimate contributions to the field. That matters because the dry slot mechanism is not a hypothesis being floated by an outsider. It is a documented, peer-reviewed, institutionally credentialed finding. The mechanism is real. The case studies are real. The pattern is consistent. And the question that has not been answered, the question that this investigation is going to put on the table, is whether the modern emergency management system has actually integrated this finding into its operational planning. To put that in human terms, when a father in Flagstaff checks his phone to see if he needs to evacuate his family, does that app know what the American Meteorological Society knows? The answer, based on what was being communicated to the public on the afternoon of June 8, 2026, appears to be no. That is the failure point that changes this from a natural event into a systemic breakdown. Let me show you what that gap looks like in practice. The Forest Service Incident Management Team running the Papa Fire had access to the spot weather forecast issued by the local National Weather Service office. That spot forecast, which is a customised weather product produced for active fire incidents, did include a reference to upper-level dynamics and the possibility of subsidence-driven dry air at the surface. The information was there. It was in the technical product that the incident commander would have reviewed during the morning briefing, but the public-facing products, the ones the evacuees and the residents and the highway travellers were reading on their phones, did not carry that information forward. The red flag warning text used standard language about low humidity and gusty winds. The forecast graphics showed temperature, dew point, and wind speed. The water vapour satellite imagery, which would have shown the dry slot clearly to a trained viewer, was not embedded in any consumer-facing product that the average resident of northern Arizona was likely to encounter. This is the gap. The institutional knowledge exists. The peer-reviewed evidence exists. The operational forecasts incorporate it, but the public-facing communication chain has not been updated to reflect what the science has known for nearly a decade. A retired physician who spent his career in emergency medicine in a hospital in Phoenix and now lives in a second home in a forested neighbourhood outside Flagstaff during the summer months, told a local newspaper reporter the morning after the fire ignited that he had checked the weather forecast 3 times on Sunday and twice on Monday before deciding it was safe to drive up to the cabin for the week. He saw the temperature, he saw the humidity, he saw the red flag warning. He made the decision a reasonable person would make based on the information available. He did not see, because no public product showed him, that the air above his cabin was descending from 25,000 feet and stripping the forest floor of its remaining moisture as he was unloading groceries from the trunk of his car. The institutional credibility of the dry slot mechanism is the linchpin of this investigation. It is not a theory, it is not a speculation, it is not an exotic claim from an unaccredited source. It is the documented finding of a professional society whose authority on atmospheric science is the highest available in the United States. And yet the finding has not been operationalized in the products that reach the people who need it most. There is a parallel here that helps anchor the point. In the early decades of weather radar, the technology was deployed at major airports and military installations long before it reached the public weather products. Forecasters at certified facilities could see severe weather forming in real time, while the general public was still relying on regional bulletins that lagged the actual storm development by hours. It took years of advocacy, technological maturation, and institutional pressure before radar imagery became a standard component of the consumer weather product. The dry slot mechanism is in a similar position today. The science is mature. The institutional acceptance is established. The translation to the public has not happened yet. The Schoeffler paper and the broader body of work it represents sits in the same category as those early radar findings. It is the kind of institutional knowledge that, once translated, will look obvious in retrospect. Future generations of viewers will see dry slot warnings on their phones and wonder how anyone ever forecast fire weather without them. But for the residents of northern Arizona on June 8, 2026, that future is not yet here. The translation has not happened. The warning is not on the phone. The institutional knowledge is sitting in a 2017 paper that almost nobody outside the field has read. The American Meteorological Society looked at all of it, ran it against the case studies, and confirmed what some had quietly suspected. The dry slot mechanism is responsible for a documented category of catastrophic fires. They do not know how many more fires fit the pattern that have not been studied. They do not know how often the mechanism is operating without being recognized. They do not know whether the institutional response will catch up to the science in time to matter. The Papa Fire is going to test that question in real time. The mechanism is over the forest. The crews are on the ground. The science is in the papers. The public is reading a red flag warning that uses 1990s vocabulary to describe a 2026 atmosphere. And the next piece of this investigation is going to show you what happens when that gap meets a fire that does not care what the consumer weather product says. Remember the core signature of the 2022 tunnel fire, which erupted under the exact same conditions we are tracking today. The tunnel fire ignited on April 17, 2022, north of Flagstaff, in the same Coconino National Forest, on a similar mix of ponderosa pine and dry understory. The fire grew from a small ignition to more than 19,000 acres in a matter of days. It destroyed 30 homes. It forced more than 2,000 residents to evacuate from neighborhoods that had stood untouched by wildfire for decades. The post-instant analysis identified the driver. It was a tropospheric dry slot, descending from the upper atmosphere, coupling to the surface, and overriding every conventional containment strategy that the responding agencies could deploy. The signature is the same. The geography is the same. The fuel type is the same. The atmospheric mechanism is the same. The only difference, 4 years later, is the calendar date and the fire name. Let me show you exactly what the 2022 fire actually did, because the comparison is not abstract. It is the closest precedent the Papa Fire has, and it is the precedent that the incident management team running the Papa Fire response is reviewing in real time as the current incident unfolds. The tunnel fire began as a small ignition near a forest road on a Sunday afternoon. The initial response was standard. Engines arrived. A small team began working the perimeter. The fire was small. The conditions on the surface looked challenging but manageable. Then the wind shifted. The humidity collapsed, and within hours the fire had grown beyond the capacity of the initial attack to contain. By Monday morning, the fire was throwing embers into the residential subdivisions north of Flagstaff. By Monday afternoon, homes were burning. By Monday evening, the Coconino County Sheriff's Office was running mass evacuations. The relative humidity readings during the most extreme growth phase of the tunnel fire dropped to 5%. 5%. That is not a typo. That is air with almost no moisture in it, behaving like the inside of a commercial dehydrator. The number matters because it crosses a threshold that fire behavior analysts treat as a marker of catastrophic potential. Below 10% relative humidity, fine fuels lose moisture faster than they can recover. Below 5%, the fuels become functionally bone dry, indistinguishable from kiln-dried lumber, and any ignition source produces sustained combustion at a rate that ground-based suppression cannot match. A 5% relative humidity reading means the air is as dry as a kiln, turning timber into instant tinder. It is not a difference of degree from a 25% reading. It is a difference of category. At 25% humidity, a fire burns. At 5% humidity, a fire detonates. The Papa Fire on June 8, 2026, recorded a relative humidity reading of 6% at one of the remote automated weather stations near the incident at 4:47 in the afternoon. By 6:30, the reading at the same station was 4%. The atmosphere over the Papa Fire was drier than the atmosphere over the tunnel fire had been at the equivalent point in its development. The fingerprint was not just similar, it was more extreme. Here is what happens to fire behavior at those humidity levels. Embers, which are small burning pieces of fuel lofted into the air by the convective column of the fire, can survive much longer in flight than they can under normal conditions. An ember that would have burned out within 30 seconds in 25% humidity can travel for 2 or 3 minutes in 5% humidity, because the surrounding air does not absorb its heat fast enough to extinguish it. That extended life translates directly into distance. An ember that can survive for 3 minutes in a 40-mile-per-hour wind can travel close to 2 miles before it hits the ground. 2 miles. Let that distance sit. The fire is here. The next ignition is 2 miles away. The containment line that ground crews spent 6 hours cutting between here and there is now irrelevant. The fire has jumped it without needing to cross it. This is the mechanism by which traditional containment lines fail under vertical dry slot forcing. A containment line works by removing the fuel between the fire and the next available fuel bed. The line is dug, cleared, scraped, or burned in such a way that there is nothing combustible inside its width. When the fire reaches the line, there is no fuel to carry it across. The fire stops, or at least slows down enough for crews to engage it directly. This is the foundation of wildland firefighting. It has been the foundation for more than a century. The dry slot mechanism breaks the foundation. It does not break it slowly. It does not break it once. It breaks it as a continuous process for as long as the slot is coupled to the surface. Embers fly. Spot fires ignite. The new ignitions become their own fires. Those fires throw their own embers. The original containment line is no longer the boundary of the incident. The incident has become a region rather than a perimeter, and the region is expanding in directions that ground crews cannot predict and cannot reach. This is why, on the afternoon of the second day of the Papa fire, the incident management team made the decision to shift from active containment to point protection. Point protection is the firefighting term for prioritizing the defense of specific structures and locations rather than trying to hold a continuous line around the fire. It is the strategic acknowledgement that the perimeter cannot be held. It is the moment when the agencies running the response say, in operational language, that they have lost the ability to control where the fire goes. They can only try to control what the fire destroys. The triple weight of this moment is the one that has to be named clearly. They can deploy the hotshot crews, they can cut the containment lines, they can dump thousands of gallons of water, but the atmosphere will override it all. The mechanism is operating from above. The crews on the ground are not failing. They are doing what they were trained to do, with the equipment they were given, against a force that the equipment was not designed to fight. A woman in her early 70s who had lived in a small subdivision on the eastern edge of Flagstaff since 1987 watched the smoke column from her kitchen window on Tuesday afternoon. Her husband had died 3 years earlier. Her 2 children lived out of state. She was alone in the house with 2 cats and a small dog. She had been through the tunnel fire in 2022. She had evacuated then. She had returned to find her home intact, but a neighbour's home, half a mile away, had been reduced to a foundation and a chimney. She knew what the smoke meant when it was that thick, that early, and that close. She started packing the same way she had packed in 2022. The tunnel fire destroyed 30 homes. The post-incident reports identified the dry slot as the primary atmospheric driver. The recommendations from those reports included calls for better integration of upper-level dynamics into public weather products, better communication of dry slot conditions to residents in fire-prone areas, and better resourcing of incident management teams operating in conditions where standard containment strategies would not work. Some of those recommendations have been implemented at the operational level. Most have not been translated into public-facing communication. That is not a failure of any one agency. That is the friction of a large institutional system trying to update its protocols faster than the protocols can be updated. It is the same friction that delayed the integration of radar into public weather products. It is the same friction that delayed the integration of satellite imagery into local broadcasts. The system catches up eventually. The question is what burns down in the gap. The Papa fire is burning in the gap right now. The relative humidity over the fire is not going to recover overnight. The dry slot is not going to dissipate on a forecaster's schedule. The atmosphere is going to do what the atmosphere is going to do, and the ground crews and the incident management teams and the evacuated residents are going to find out together what the outcome looks like. The crews are doing everything they can. The agencies are coordinating everything they can. The technology is being deployed at the limits of what the equipment can sustain. And the limits, as the next piece of this investigation is going to show, are the next part of the story. Let me ask you a question that highlights the hidden friction inside modern emergency operations. Why do the most advanced firefighting aircraft in the world stay on the tarmac when they are needed most? The question sounds counterintuitive. The aircraft exist, the crews are trained, the retardant is loaded, the infrastructure is funded, and yet, on the second day of the Papa fire, with ground crews falling back from containment lines and homes coming under threat, the heavy air tanker fleet and the helicopter fleet were largely grounded. Not by mechanical failure, not by lack of fuel, not by lack of crews, by the same wind that was making the fire impossible to contain. The mechanical rules governing wildland firefighting aircraft are not arbitrary. They are the product of decades of operational experience, painful losses, an engineering analysis that has converged on a set of thresholds beyond which the aircraft cannot safely operate. The thresholds are not suggestions. They are hard limits, written into the operational procedures of every federal contracting agency that hires firefighting aircraft, and into the safety protocols of every pilot certified to fly them. The first threshold is wind speed. Heavy air tankers, which include aircraft like the BAE-146, the C-130, and the converted commercial jets used in the modern firefighting fleet, are generally restricted from operating when sustained winds at the drop altitude exceed 25 miles per hour, with gust thresholds even tighter. The reason is straightforward. These aircraft fly at low altitude over rough terrain, releasing thousands of gallons of liquid retardant from a few hundred feet above the canopy. The maneuver requires precise altitude control, precise heading control, and predictable airflow. Strong winds, especially gusty winds, make all three of those requirements impossible to maintain with the safety margins the operation requires. The second threshold is visibility. The retardant drops have to be placed accurately to be effective. A drop that misses the target by 100 yards is essentially wasted. The pilot needs to see the ground, see the target, and see the surrounding terrain clearly enough to plan an escape route after the drop. Heavy smoke, especially the dense, turbulent smoke produced by a high-intensity wildland fire, can reduce visibility below the operational minimum within minutes. When visibility drops, the aircraft are pulled back. The third threshold is turbulence. A fire of the intensity that the Papa fire reached on its second day produces its own weather. The convective column rising from a high-intensity fire can generate vertical air movements of dozens of miles per hour, with shifting horizontal components that vary unpredictably across the fire perimeter. Flying through that turbulence at low altitude with a partial fuel load and a partial retardant load is not a maneuver that the aircraft are certified for. The aircraft will tear apart. The crews will be lost. Helicopters operate under similar but distinct rules. Type 1 heavy helicopters, the large rotor-wing aircraft that drop water or retardant from suspended buckets or fixed tanks, can sometimes operate in slightly higher wind conditions than fixed-wing tankers, but they have their own envelope limits. Their bucket operations become unreliable when crosswinds exceed certain thresholds, because the suspended bucket begins to swing in ways that compromise the accuracy of the drop. Their fixed tank operations require slow, low-altitude flight patterns that become dangerous in turbulent air. When sustained winds reach the 50 to 65 mile per hour range that the Papa fire was experiencing on its second day, the entire fleet is grounded. Not because the aircraft cannot physically fly. They can. Commercial airliners fly through those wind conditions at altitude every day without incident. The grounding is because the specific firefighting mission, which requires low altitude, low speed, precise placement, and predictable airflow, cannot be performed safely under those conditions. The aircraft sit on the tarmac. The crews stand by. The fire burns without aerial intervention. This is the operational reality that the public rarely sees. The image of a wildland fire response, the one that dominates television coverage, is the image of the slurry bomber rolling in over the ridge, dumping its red payload across the flame front, and pulling up dramatically against a sky stained with smoke. That image sells the public on the idea that aerial firefighting is a primary tool. In reality, aerial firefighting is a supplementary tool that works under specific atmospheric conditions. When those conditions are absent, The tool is unavailable. The dry slot mechanism produces exactly the conditions under which aerial firefighting cannot operate. The wind speed is too high. The turbulence is too severe. The fire intensity driven by the desiccated fuels under the slot produces convective columns that no pilot will fly through. The very atmospheric event that makes aerial intervention most needed is the same atmospheric event that makes aerial intervention impossible. The hotshot crews on the ground are left without aerial support during the precise hours when they need it most. A hotshot crew is a 20-person team of highly trained wildland firefighters, organised for sustained high-intensity work in remote terrain. They are the elite ground force of the federal wildland firefighting system. They carry their own water, their own food, their own tools. They work for days at a stretch, in conditions that would defeat less prepared crews. They are not the same as the structure firefighters who respond to house fires. They are specialists, and the specialty they have mastered is the engagement of wildland fire in rugged backcountry. Even hotshot crews have limits. When aerial retardant drops are unavailable, the crews have no way to slow the rate of spread of a high-intensity fire from a distance. They can only engage at close range. Close-range engagement, on a fire that is throwing embers a mile or more ahead of its front, is not a viable tactic. The crews would be flanked. The crews would be cut off. The crews would be killed. So the crews do not engage at close range when the dry slot is coupled. They withdraw to defensible positions. They protect structures where they can. They monitor the spread and report the position of the front. They wait for the wind to ease, the humidity to recover, the convective column to settle. They wait for the dry slot to lift off the surface and give the atmosphere back to the standard diurnal cycle. They wait because waiting is the only safe response. The fire grows during the wait. A hotshot superintendent from a crew based in southern Arizona, who was redeployed to the Papa fire on the second day, told a regional news outlet later in the week that the conditions on Tuesday afternoon were the worst he had encountered in his career. His crew had been on the line for 8 hours. They had cut a containment line on the northern flank of the fire. They had watched embers from the fire travel over their line and start 3 new spot fires behind them within the span of 20 minutes. They had withdrawn to a paved road and a parking area at a trailhead, regrouped, and been assigned to structure protection in a residential area near the highway. By sunset, 2 of the 3 spot fires they had watched had merged into a new finger of the parent fire. By midnight, the finger had pushed close to a county road that crews had hoped to use as a backup containment. The aerial assets during all of this were on the tarmac at the Prescott Regional Airport and at staging areas in northern Arizona. The crews were ready, the aircraft were fueled, the retardant was loaded, the conditions made the flights impossible. The same dry slot that had stripped the moisture from the forest had grounded the only tool capable of laying retardant ahead of the fire from above. This is the vulnerability that the modern firefighting system has not solved. The aircraft are essential to the standard playbook. The standard playbook assumes the aircraft will be available when the fire is most active. The dry slot mechanism inverts that assumption. The fire is most active precisely when the aircraft are most grounded. The 2 variables, fire intensity and aircraft availability, move in opposite directions under dry slot forcing, and the system has no current solution to that inversion. There are research programs exploring unmanned aerial systems, ground-based water delivery, and other alternatives that might operate in conditions where conventional aircraft cannot. The research is promising, but unfinished. The technology is years away from operational deployment at scale. For the residents of northern Arizona on June 8, 2026, the technology that might solve this problem is not yet here. The technology that exists is grounded. The vulnerability is not just operational. It is also financial, structural, and political. The federal contracting system that hires firefighting aircraft is built around an assumption of availability. The contracts pay for standby time and flight time. When the aircraft cannot fly, the standby costs continue to accumulate while the public watches a fire grow without visible intervention. The political pressure that builds during such periods is intense. Governors ask why the planes are not flying. Members of Congress ask why the federal response is inadequate. The agencies running the response have to explain again and again that the planes are not flying because the planes cannot fly, and the explanation never satisfies the political pressure that demands visible action. The dry slot, sitting silently above the fire, is the source of both the fire and the inability to fight it from the air. It is the same mechanism. It is the same column of descending dry air. The fire is the visible symptom. The grounded fleet is the operational consequence. And the people who pay the price are the residents on the ground, watching the smoke and waiting for an aerial response that the atmosphere will not allow. But while everyone is looking up at the empty sky, a completely different system is failing just out of sight, and it threatens millions of people who are nowhere near the flames. While ground crews face the immediate threat of smoke and flame, federal infrastructure monitoring systems are tracking a completely different set of coordinates just east of Flagstaff. The maps used by infrastructure analysts do not show the fire perimeter the way the public maps show it. They show transmission corridors, substation locations, pipeline rights of way, and the precise geometry of how the regional power grid and the regional natural gas network thread through the same forested terrain that is currently on fire. The intersection of the Papa fire perimeter with that infrastructure footprint is the second-order story that the local coverage has not yet reached. Let me map out the local geography. The Coconino National Forest east of Flagstaff is not empty wilderness. It is laced with high-voltage transmission lines that move electricity from generation sources in the Four Corners region and the desert southwest to consumers in California, Nevada, and the Pacific Northwest. It is crossed by natural gas pipelines that move fuel from production fields in northwestern New Mexico and southwestern Colorado toward distribution networks that serve major metropolitan areas. The corridors are wide. The capacity is enormous. The redundancy is limited. The Western Area Power Administration, which is a federal agency under the Department of Energy, operates and maintains a network of high-voltage transmission lines across 15 states. Its responsibility includes some of the largest transmission corridors in the western United States, carrying power across long distances at voltages ranging from 115 kilovolts to 500 kilovolts. Several of those corridors pass through northern Arizona, and several of those corridors run within a few miles of the current Papa fire perimeter. A high-voltage transmission line does not have to be touched by flame to be taken offline by a wildfire. Smoke is a conductor. Heavy, dense, ionized smoke from a high-intensity wildland fire can cause electrical arcing between the conductors of a transmission line, even when the line itself is well above the visible smoke layer. Arcing trips the line. Tripped lines remove capacity from the grid. The grid, if it cannot reroute the lost capacity through other paths, has to shed load. Load shedding, in practical terms, is rolling blackouts. The 2003 Northeast blackout, which left more than 50 million people without power across 8 US states and parts of Canada, began with a transmission line tripping in Ohio after contact with a tree. The cascade that followed took 8 seconds to spread across the grid. 8 seconds. The lesson from that event, which became foundational for the way grid operators think about transmission vulnerabilities, was that a single point of failure in a high-capacity corridor can trigger cascading outages across vast regions if the redundancy is not sufficient to absorb the loss. The transmission corridors through northern Arizona feed into a network that supplies major American population centers. Loss of capacity in those corridors does not stay local. The compensating power has to come from somewhere, which means generation sources further upstream have to ramp up, which means demand from downstream regions has to be balanced against available supply, which means decisions about who gets power and who does not start moving up the chain to grid operators in regions far from the actual fire. A localized blaze on the Coconino Ridge can, in extreme cases, contribute to power decisions affecting consumers in cities hundreds of miles away. This is not theoretical. In 2020, a series of wildfires in California caused public safety power shutoffs that affected more than 3 million customers. The shutoffs were preemptive, ordered by utilities in coordination with regulators to reduce the risk of additional ignitions from energized lines in high fire risk conditions. The pattern, once established, has become a recurring feature of the Western fire season. The Western Area Power Administration corridors near the Papa Fire perimeter are not yet at that threshold, but the analysts watching those corridors are running the same calculations that the California utilities ran in 2020. The natural gas pipeline infrastructure introduces a different set of risks. The pipelines themselves are buried, generally below frost depth, and are not vulnerable to direct flame contact in the way that overhead transmission lines are. But the surface facilities, including compressor stations, valve stations, and metering stations, are above ground and are vulnerable to wildfire damage. A compressor station that loses power, loses cooling, or sustains direct heat damage can be taken offline for days or weeks. The pipeline downstream of that station can lose pressure or be shut down entirely as a safety precaution. The pipelines crossing northern Arizona carry natural gas to electricity generation facilities, to industrial customers, and to residential distribution networks across the Southwest. Interruption of supply on those pipelines does not produce the immediate visible drama of a power outage, but it produces a slower, deeper, and often longer-lasting disruption that ripples through energy markets and through dependent industries for weeks after the initial event. A retired infrastructure engineer who spent 30 years working on natural gas transmission systems before retiring to a small community on the outskirts of Flagstaff was watching the news coverage of the Papa Fire on Tuesday morning. He recognized the perimeter geometry. He pulled up a publicly available pipeline route map on his computer and overlaid it mentally with the fire location reported by the Forest Service. He saw that one of the major regional pipelines passed within roughly 4 miles of the active fire front. He saw that a compressor station on that pipeline sat at a location that, if the fire moved in a particular direction, could come within striking distance of the structure by Thursday or Friday. He made a list of phone calls. He started making them. The federal infrastructure monitoring systems that track these vulnerabilities are not generally accessible to the public. The Department of Energy operates a center that monitors energy infrastructure threats in real time, with feeds from utilities, pipeline operators, and federal agencies. The information it produces is shared at the operational level with relevant stakeholders, but it is not packaged for consumer consumption. The general public, watching the fire on the local news, has no visibility into the infrastructure analysis happening in parallel to the firefighting response. The intersection of the Papa Fire with the regional infrastructure is the kind of story that emerges fully only after the incident is over. The post-incident reports will catalogue which lines tripped, which compressor stations were threatened, which transmission corridors had to be derated, which downstream customers experienced disruptions. The reports will sit on websites and in archives. They will be read by analysts. They will not generally be read by the public. But the public is the one paying the bill. Power rates absorb the cost of grid hardening, of transmission corridor maintenance, of compressor station replacement, of wildfire mitigation programs run by utilities. Gas rates absorb the cost of pipeline integrity programs, of compressor station resilience upgrades, of supply diversification. When a wildfire takes infrastructure offline, the cost of restoring that infrastructure is socialized across ratepayers across the affected service territories. The flames currently consuming the Papa Fire perimeter are going to show up in utility bills across the Southwest, in ways that the ratepayers will not connect to the fire when the bills arrive. The upper atmosphere mechanism, the dry slot that this investigation has been tracing from the beginning, is now operating as a multi-state economic force. It started as an atmospheric phenomenon. It produced a wildland fire. The wildland fire threatened infrastructure. The threatened infrastructure runs across state lines. The economic consequences of any disruption ripple across millions of customers across multiple states. a column of descending air originating in the upper troposphere over the eastern Pacific, is now connected directly to electricity bills in Los Angeles and natural gas costs in Las Vegas. The cascade is the point. The cascade is what infrastructure analysts watch. The cascade is what the institutional monitoring systems are designed to interrupt before the dominoes start falling. The question on the second and third day of the Papa Fire is whether the cascade can be interrupted by the same agencies that are simultaneously trying to manage the fire on the ground, the evacuated residents, the political pressure, and the economic costs of the response itself. That is not the kind of question that gets answered in a single news cycle. That is the kind of question that gets answered in the post-incident reports months later, when the analysts have the data and the time to trace the chain. But for the residents who are watching the smoke from their kitchen windows in Flagstaff, in Sedona, in Williams, in Winslow, the question is more immediate. Their lights are still on. Their gas is still flowing. The infrastructure is still holding. And the silent calculation of how long it can keep holding against an atmospheric mechanism that the institutions are still learning to forecast is happening in offices and operations centres far from the visible fire. But there is a second group of Americans caught in this zone right now, and the standard warnings completely failed to tell them what they were driving into. Consider the immediate reality facing thousands of travellers who are currently driving high-profile recreational vehicles along the interstate corridors of northern Arizona. Interstate 40, the main east-west highway across the northern third of the state, runs directly through the region affected by the dry slot conditions that are driving the Papa Fire. It is one of the busiest summer travel corridors in the United States, carrying tourists, retirees, long-haul truckers, and commercial freight across the country between the Pacific coast and the Midwest. On any given day in June, the highway carries tens of thousands of vehicles. On a day with active fire weather and crosswinds in the 50-mile-per-hour range, the highway becomes a hazard zone for an entire category of vehicles that the standard travel advisories do not always address with the urgency the conditions require. High-profile recreational vehicles, which include the large motorhomes and travel trailers favoured by retirees on summer trips across the West, are particularly vulnerable to crosswinds. The flat side of a 30-foot motorhome presents a massive surface area to the wind. The centre of gravity is high. The wheelbase, relative to the height, is narrow. Crosswinds in the 40 to 50 mile-per-hour range produce a steering challenge that can exhaust an experienced driver within an hour. Gusts in the 60 mile-per-hour range can push a motorhome into the adjacent lane, or, in the worst cases, can roll the vehicle entirely. The Arizona Department of Transportation has issued advisories during high wind events for years. The advisories are standard. They recommend that drivers of high-profile vehicles reduce speed, increase following distance, and consider postponing travel if conditions exceed personal comfort levels. The advisories are accurate. They are also, in the way of all standard advisories, calibrated to the kind of high wind event that the historical record has produced. The current event, driven by a tropospheric dry slot that is delivering sustained winds well above the historical norm for this region in early June, is testing whether the standard advisories are sufficient. Two retirees in their late 60s, travelling from Southern California to a family reunion in the Midwest, were driving a 32-foot motorhome eastbound on Interstate 40 on Tuesday afternoon. They had checked the weather forecast that morning at a rest area near Kingman. They had seen the wind advisory. They had decided, after some discussion, that they could manage the conditions and continue toward their planned overnight stop in Albuquerque. By the time they reached the high country east of Flagstaff, the wind was no longer something they could manage. The motorhome was being pushed across the lane on every gust. The driver, the husband, gripped the wheel with both hands and dropped his speed to 40 miles per hour, then to 30. Then began looking for an exit ramp where he could pull off and wait out the conditions. He found one near the small town of Winslow. He pulled into a truck stop. He sat in the parking lot with the engine running and his wife in the passenger seat for the next 4 hours. The truck stop, by the end of Tuesday afternoon, had filled with high-profile vehicles whose drivers had made similar decisions. The parking lot, designed for tractor-trailers and a handful of passenger vehicles, had been overrun by motorhomes, travel trailers, and pickup trucks pulling tall cargo trailers. The truck stop manager, a woman in her 50s who had worked at the location for over a decade, was making phone calls to her regional office trying to figure out what to do with the overflow. She had seen busy days before. She had never seen the parking lot completely filled by mid-afternoon by vehicles that were not actually buying fuel because they were too afraid to drive. The socio-economic toll of the conditions extends beyond stranded travellers. The Coconino National Forest has been placed under Stage 1 fire restrictions, which prohibit campfires outside designated developed campgrounds, restrict smoking to enclosed vehicles or developed sites, and limit certain equipment uses that could produce sparks. Stage 1 restrictions are the lowest level of formal fire restriction in the federal land management system. Stage 2 restrictions, which the forest may move to depending on conditions, would prohibit all open flames outside developed areas and would close certain forest roads and trails to public use. Stage 3 restrictions, which would close the forest entirely, are the most severe and are imposed only under extreme fire danger. The Coconino National Forest receives several million visitors per year. The summer season is the peak. Local economies in Flagstaff, Sedona, Williams, Page, and a dozen smaller communities depend heavily on tourist revenue that flows from those visitors. Campgrounds, outfitters, restaurants, hotels, and retail businesses all see their annual revenue peak in the summer months. Fire restrictions, even at Stage 1, suppress demand. Travellers cancel reservations. Outfitters lose bookings. Restaurants see slower nights. The economic effect is real, immediate, and concentrated in communities that often have limited options to make up the lost income later in the year. A small family-run outfitter in Flagstaff, which has been guiding hiking and backpacking trips into the surrounding wilderness areas for 3 generations, lost a third of its bookings within 48 hours of the Papa Fire ignition. The cancellations came in by phone, by email, and through the booking platforms the business uses. Some of the cancellations were from groups who had been watching the news coverage and decided not to come. Some were from groups whose trip plans had been disrupted by trail closures or smoke advisories. The owner of the business, a man in his mid-50s whose father had started the outfit in the 1960s, sat at his desk on Wednesday morning and tried to do the math on whether the lost revenue could be made up by extending the season into the fall. The forecast updates that are coming over the next several days will determine how long the restrictions remain in place, how long the highway advisories remain active, and how long the public-facing communications will need to maintain the heightened warning posture. The National Weather Service issues an area forecast discussion several times per day, which is a technical document that explains the reasoning behind the public forecasts and includes the kind of upper-level analysis that this investigation has been tracking. The discussion is publicly available. It is read by meteorologists, by emergency managers, by infrastructure analysts, and by a small number of enthusiasts who follow weather closely. It is not read, generally, by the public. The area forecast discussions from the Flagstaff office over the past several days have included explicit references to the dry slot conditions, the long-wave trough pattern, the expected duration of the upper-level subsidence, and the probable timing of any pattern change that would relax the conditions. The information is there. The information is detailed. The information is not, however, packaged for consumer consumption in a way that would help the motorhome driver at the Winslow truck stop, or the outfitter in Flagstaff, or the family debating whether to keep their reservation at a campground near Sedona. The translation gap, which this investigation has been documenting from the start, shows up here as a practical consequence. The technical product is robust. The consumer product is thin. The people most affected by the conditions are the ones with the least access to the underlying analysis, and the next 24 to 48 hours, as the dry slot either persists or begins to dissipate, will play out for those people as a series of decisions made on incomplete information, while the institutions running the response continue to operate on a more complete picture that the public cannot see. The forecast update is not just a piece of paper. It is the point at which the institutional understanding of the atmosphere either reaches the public in time to inform their decisions, or arrives too late to matter. The next discussion is scheduled. The meteorologists are assembling the data. The area forecast discussion will be released, posted to a federal website, and made available to anyone who knows where to look. The question is whether anyone who needs the information will actually find it before the next decision they have to make. Because what that forecast will ultimately reveal is an hour of absolute no return that the entire southwest is hurtling toward. The next 24 hours will completely determine the trajectory of this disaster, as meteorologists at the National Weather Service prepare to release their next definitive model update. The update is not a single document. It is the integration of multiple model runs, multiple observational data sources, and the human judgment of meteorologists who have been watching this pattern develop for the better part of a week. The update will land in the morning briefing for the incident management team. It will inform the operational decisions for Wednesday and Thursday. It will determine whether the dry slot is forecast to persist or to lift off the surface. The exact atmospheric developments required to break the dry slot pattern are not complicated to describe. The long-wave trough that has been anchoring the descending air mass over the southwest needs to move. The jet stream, which has been holding the trough in place through a stable upstream flow pattern, needs to shift. The downstream ridge, which has been blocking eastward movement of the trough, needs to weaken. When those three things happen, the geometry that has been forcing upper air down to the surface over northern Arizona will relax, and the standard diurnal humidity cycle will resume. The metrics that will determine whether the long-wave trough finally exits the region are specific. Meteorologists will be watching the 500 millibar height field, which is a map of the pressure pattern at roughly 18,000 feet. They will be watching the position of the jet stream maximum, which is the core of the strongest winds at the top of the troposphere. They will be watching the moisture profile in the satellite water vapor imagery, looking for the dark, dry streak to either move east or weaken in place. They will be watching the surface dew point readings, looking for the first hint that moisture is returning to the boundary layer. The model guidance over the past 24 hours has been suggesting with moderate confidence that the pattern will begin to break by Thursday afternoon or Friday morning. The confidence is moderate, not high, because the timing of pattern changes in the western United States is notoriously difficult to forecast precisely. The trough may move on schedule. The trough may stall for an extra 12 to 24 hours. The trough may move and be replaced by a second, weaker trough that maintains some level of subsidence over the region for several additional days. The model spread, which is the range of possible outcomes across the various forecast models, is wider than the meteorologists would prefer for this kind of high-stakes operational decision. The next area forecast discussion will narrow the spread. The meteorologists will have access to the overnight model runs, which incorporate the latest satellite observations and weather balloon data. They will compare the new runs against the previous runs. They will identify which model is performing best for this particular pattern. They will issue their best assessment of the timing. The incident management team running the Papa Fire response will use that assessment to plan the next operational period. If the dry slot is forecast to lift by Thursday afternoon, the team will plan an aggressive engagement phase for Friday, with full deployment of aerial assets and a coordinated push to establish containment lines on multiple flanks. If the dry slot is forecast to persist into the weekend, the team will plan a sustained defensive posture, with continued point protection of structures and continued evacuation of additional areas as the fire perimeter expands. The forecast is not just a weather product, it is the input to a series of decisions that will determine which structures get protected, which crews get deployed, which evacuations get expanded or rescinded, and which infrastructure corridors get harder protection. The decisions will be made by humans based on the best available data in conditions of significant uncertainty. The decisions will be evaluated, after the fact, in post-incident reports that will sit on shelves for years. The hour of absolute no return is the hour at which the forecast either confirms a pattern break or extends the dry slot into a longer time window. Once that confirmation lands, the operational plan locks in. The crews move. The aircraft are positioned, or not. The evacuations are expanded, or not. The infrastructure protection assets are deployed, or held in reserve. The decisions cascade from a single piece of forecast text into 1,000 operational consequences across northern Arizona. The residents waiting in evacuation shelters, the travelers parked at truck stops along Interstate 40, the outfitters watching their bookings collapse, the infrastructure operators monitoring their transmission lines are all waiting on the same forecast. They will not all read it, they will not all understand it, but they will all feel its consequences in the hours and days that follow its release. The atmosphere over northern Arizona, in those hours, will be doing what it has been doing for the past several days. The dry slot will continue to descend, the wind will continue to press. The humidity will continue to sit at single digits during the warm hours and recover only partially overnight. The fire will continue to grow, slowly under the calmest hours and aggressively under the hottest. The forecast update will not change any of that immediately. The forecast update will only tell the people running the response how much longer they have to endure it. And it will finally force us to answer the single most terrifying question of this entire event. What exactly is pushing these invisible columns down onto our cities in the first place? We are back where we started, looking past the smoke of a 135-acre fire and staring directly into the descending column of air that connected the upper atmosphere to the desert floor. The fire on the ground is real. The acreage is real. The evacuations are real. But the deeper image, the one this investigation has been building toward, is the image of an invisible river of dry air pouring downward from the edge of the stratosphere, finding the forests of northern Arizona, and rewriting the rules of how a wildfire behaves under modern conditions. The Papa fire is not the first time this has happened. The Tunnel fire in 2022 followed the same pattern. The Wallow fire in 2011 followed the same pattern. The Hayman fire in 2002, the Cerro Grande fire in 2000, the Buffalo Creek incident in 1996 all followed the same pattern. The mechanism has been observed for decades. The case studies have piled up year after year. The fingerprint has not changed. What has changed is the frequency. The technical papers from the past decade have begun to document an upward trend in the number of days per fire season when upper-level subsidence reaches the surface with sufficient intensity to override the standard humidity cycle. The pattern is not local. It is not confined to Arizona. The same mechanism has been documented over fires in California, in Oregon, in Idaho, in Montana, in Colorado, in New Mexico, in Utah, in Nevada. The dry slot, in the way it is now being observed across the western United States, is not an Arizona problem. It is a southwest problem. It is a western problem. It is, in the larger picture, a symptom of changes in the global circulation pattern that drives the jet stream itself. The jet stream has been changing, the data is in, the peer-reviewed literature across multiple disciplines has documented that the polar jet stream is becoming wavier, slower, and more prone to anchoring deep troughs over particular regions for longer periods than the historical record would suggest. The reasons for those changes are still being argued in the academic literature, but the observational reality is settled. The jet stream of 2026 is not the jet stream of 1986. The wave patterns are different. The persistence is different. The downstream consequences, which include the kind of dry slot coupling events that drove the Papa fire, are different. This is no longer just a local forecast. It is a planetary alarm bell ringing directly over the forests where Americans live, work, and retire. The 135-acre fire east of Flagstaff is a small fire by historical standards. The acreage will likely grow before it is contained. The structures lost, if any, will be tallied in the post-incident report. The cost of the response will be added to a federal budget line that has been growing every year for the past 2 decades. The lessons learned will be added to the institutional knowledge that fire management agencies maintain, and the next time a dry slot couples over the Coconino National Forest, or over another forest in the west, the same cycle will repeat. The investigation has traced the chain from the visible fire to the invisible mechanism, from the local incident to the regional infrastructure, from the surface map to the upper air analysis, from the consumer weather product to the peer-reviewed technical literature. The chain is complete. The chain is documented. The chain has been operating in plain sight for anyone who knew where to look. The question that remains is whether the institutional response will catch up to the science, whether the consumer products will catch up to the operational forecasts, whether the public will gain access to the same picture that the analysts have had all along. The smoke over Flagstaff on the night of June 8, 2026, was visible from satellites in orbit. The dry slot above the smoke was visible on the water vapor imagery from those same satellites. The 2 images side by side told the entire story. One image was on the evening news, the other image was on a federal website that almost nobody visited. The heat is real, it is measured, it is already here, and it is already moving. When we look at the blackened slopes outside Flagstaff, we are no longer just looking at a localized wildfire, but rather staring at the visible footprint of a changing atmosphere that is now reaching down from the edge of space to reshape our world.